All right, as everybody's coming in and get settled, we're just going to give it another minute just to let anyone who hasn't connected yet get set up, and then we'll get started with today's talk. Welcome. This is the How To Talks by Postdocs mini series. So you are in the right place if that's where you intend to be. All right. So, like I said, this is the How To Talks by Postdocs mini series. I am Dr. Stacy Wall. I work within BCU Libraries as the liaison to the basic sciences on the Health Sciences campus. Today is the first of our virtual How To Talks mini series. So for the month of March, every Monday at noon, there will be a How To Talk where a postdoc will come and share about how to do something. And today we have our kickoff with Dr. Lisa Roger, and I'm pretty excited about this talk, friends. So Dr. Roger grew up on the coast of Normandy, where she loved playing in rock pools at low tide and became passionate about the ocean after seeing her first underwater documentary. Dr. Roger then studied marine biology and coastal management in France and obtained her PhD in Western Australia at the Institute of Marine Science. After graduating, she continued to explore all things ocean related, including being a whale watching tour guide in Iceland and a scuba instructor in Greece. She joined Dr. Lewinsky's lab in the Department of Chemical and Life Sciences Engineering in the College of Engineering last March and has enjoyed getting into her new projects. Today, she will be talking to us about regional climates and using that data from the past to predict the future. So I'm going to turn it over to Dr. Roger.
Thank you very much. So I'll just share my screen with you. This is the one. Can everybody see my screen? Yes. Okay. So there we go. Thank you very much for the introduction, and thank you everybody for being here today. So like Stacy said, I have a PhD in marine biology and geochemistry, and geochemistry stands for the composition of minerals. And so I did that in Western Australia. It was amazing. I highly recommend Western Australia if you ever have a chance to go. And at the moment, I am a postdoc in Dr. Lewinsky's lab in the College of Engineering. So the work what I'm talking about today is more related to what I did during my PhD in Australia. And what I'm doing at the moment with my postdoc will be the topic of my next talk on the 15th of March. So yes, you might be interested in following that one as well if you're interested in marine stuff. And so today's talk, I'm going to talk about regional climates and how we collect data for this. But I'm going to start with focusing on how you get your daily weather forecast, for example. And I'm going to move on to how we get planet scale dynamics of the climate and how we do reconstructions of the climate to understand past and future changes. I'm going to focus especially on one tool that might be unusual to people who are not familiar with marine science in general or climate reconstructions. So I hope you're going to enjoy. So first of all, your daily climate, your weather forecast, what you get on your phone today is pretty miserable in Richmond, if everybody's in Richmond. But basically the way they get all these data together is a combination of instruments that are deployed on the planet and in space as well. So you've got satellite data, you've got climate weather stations, you have radar, you have weather balloons as well. And in relation to the data that you could collect at sea, there is moorings and AUVs. So AUVs are underwater automated vehicles, the other way around, automated underwater vehicles. And so you deploy those and you tell them where to go, and they will take measurements underwater, pop up to the surface to transmit the data. So when you combine all these data sets, you manage to get a quite accurate weather forecast. And this army of instruments, not all together, they came at different times depending on the technology, but we've been measuring climate information for at least half a century now. So by combining all of that, we managed to get planet scale dynamics. We managed to identify them and understand them. This is an example of a planet scale dynamic. So it's called the El Nino La Nina oscillation. It is centered along the central East Pacific. So you can see here where it says El Nino La Nina. So La Nina is set up for conditions where that part of the Pacific is cooling, and El Nino is the opposite. It's where it's warming. So mainly the surface ocean. This oscillation between the two trends changes between 3 to 7 years, every 3 to 7 years. And it has a lot of impacts on not only the neighboring countries, so the border countries of the Pacific Ocean, but also on the rest of the planet. So as you can see on the diagram on the right, so in the El Nino conditions, when the surface ocean is warming, so there's a lot of evaporation because hot air rises. When it's into the atmosphere, it cools down and drops again, but further along because of the winds. So then that's when you have massive floods, you have more intense monsoon events as well. You have stronger winds because of all this circulation. So it doesn't just affect the countries around the Pacific, it affects India, it affects Africa, a whole load of countries like that. And it's important for us to understand these dynamics because we get more information about what could happen. So for example, we know that because of the greenhouse effect, there is increased, so the atmosphere is heating up, and we know that the ocean absorbs this heat. So that creates heating of the surface ocean, and that's a separate phenomenon from the El Nino La Nina, but basically surface waters are heating, and not all marine ecosystems can handle changes in their temperature ranges. They have these little niches of temperature which they like, and when you diverge from them, they get upset. And so if we can predict which areas of the planet are heating or cooling, because both phenomena are happening at the same time, we can then predict which ecosystems we should focus on to understand the variations, whether we can help their resilience, or if we can preserve them and protect them so that they can stay the same for longer, or keep on going basically through changes. For example, here you have a map of the heating of the ocean, or the surface ocean, between 1993 and 2019. And you can clearly see from the color ranges, so blue is cooling down and red is heating up, red-orange is heating up. You can see both are happening simultaneously. But if you look at the resolution, for example, if we try to take a look at Chesapeake Bay, you can see there's a general warming, but we don't have any details about that. So that's a problem, the coarseness of the data that we get, or the predictions that we can get. We're missing key regional features. For example, if you have a mountain range, it's going to influence the weather forecast in that specific area because it creates microclimates. If the atmosphere is warmer, you're going to have more ice melting, and the melted ice is more fresh water that adds to the seawater. That changes the balance, and it's going to change your currents as well. There's many, many regional features that don't get measured through the instruments we have deployed at the moment. So that's when we need something else, basically. So as an example of the regional issues we might have, I'm going to take you to a very special place to meet. Here it is. This is Ningle Reef. So just absorb the image for a minute. It's very, very pretty, that place. And so Ningle Reef is located in Australia. It's on the west coast of Australia. I'm biased, that's where I did my PhD. And so this photo really shows you the landscape right there. You have the arid land, then you have the Barrier Reef. So it's not the Great Barrier Reef, it's a different reef. It's Ningle Reef. Barrier Reef is on the east coast, in case you were wondering. Then you have the open ocean, and in the middle we have the lagoon. So in this sort of scenario, where would you have the instruments? And how do you know whether the temperature of the seawater is rising, for example? So if we think about the instruments that I mentioned before, first would be weather stations. Where would you have the weather stations? So yes, Australia is huge. It will have weather stations out there, but there's a lot of desert land in Australia. So they have some, but they don't have them everywhere. Then it would be the satellites. Where are the satellites? The satellites would be able to focus on Mingle Reef, but they wouldn't give you the resolution that you want. This is quite a small area if you look at it. Then you'd have the moorings. Where would be the ocean moorings? They would be in the open ocean, unfortunately. You don't really put that many moorings inside a lagoon, whereas the lagoon is the ecosystem that could be really threatened by the rising of seawater temperatures. So we've got a problem. How do we get information here? So this is when we turn to corals. So corals are really cool little organisms. They are colonial and clonal. So colonial is because they form colonies of individuals, and clonal is for they make clones of themselves. So if you look on the drawing on the right, you have two. So these would be two clones basically. One of them is called a polyp. So then you have clones of the same polyp side by side. They have these tentacle-like structures, and they look a lot like anemones, if you know what an anemone is. They are very small, and you can't always see the detail of the tentacles if you go diving. They build these really neat calcium carbonate structures. Calcium carbonate is limestone or chalk. It's the same composition. And so they build them layer by layer. So they put one layer down and then they grow at the same time, basically. And the way they build this calcium carbonate skeleton is by using the different elements from the seawater. And so if you look at the photo on the left here, this is a coral bommy. It's just because of the shape that we call it a bommy. And here you actually have two different species that grow together on it. So you have a branching species down here and a little bit here. And then you have the massive coral here. So it would be two different types. And the one we're interested in is not the branching one, because it makes quite short branches, but it's more the massive one here. As you can see with the size of the diver, this is quite a big one. And so to remind everybody, if you ever go scuba diving or snorkeling and you see these coral structures, they're not rock, they're alive, so please don't step on them. We like them the way they are. And so once we found ourselves a nice big bommy like this, we strap it up. So we take our equipment, we go scuba diving, and we put on this frame and this guide. After that, oh, and by the way, may I introduce you to some colleagues of mine. So we have Sana here in the background. We have Juan Pablo and Mark here. So the people I did some work with up at Mingle Reef in Australia. So we put the guide on. Here's the guide a little bit more close up. So we want it level and everything, and it's really tightly strapped onto the coral, which is quite solid, so we're not damaging it. Then we bring in the drill, because what we're trying to get is a core out of this coral. And here you can see Juan Pablo's got is holding the drill barrel, which is a cylinder basically. And then up here you have the hand drill, and it's linked to a dive tank at the surface. So the air is what is making the drill work. After that, we start drilling. So again, this one is this bommy here is a little bit smaller than the one I showed before. But if you look at the size of Juan Pablo here, is about 5'8". So you can imagine that this bommy is 5'9", 6 feet, something like that. So still quite big. And then here comes the treasure. As you can see, there's some lines here across the core, which I explained before. So it's when the coral grows layer by layer. And you have living tissue at the top here. So the only part that is living is this little section up there. If you want a neat comparison to understand the thickness of the tissue of the coral, imagine putting a latex glove on your hand. The thickness of the latex glove would be the thickness of the tissue that is covering the coral skeleton. And so everything else is the dead skeleton. We are interested in the dead skeleton, not the live tissue. And we are only taking a small fraction of it, so it's not damaging the colony as a whole. And to not leave a gaping hole in this giant bommy, we put a plug, we put a cement plug to protect it. Afterwards, we take our core back home and we slice and dice, and we get these really neat images. So the top one is the top two actually are done with X-rays, so the same type of machines that you use when you were 5 years old and you broke your arm falling off your bike. Yes, it's the same stuff, and you can see these nice little layers across. The other photo at the bottom here is, so we expose the core to UV light, and we get fluorescence back. Back in the days, they used to take smaller bommies, so ones that they could carry, and they made slices out of them. So in the same way that we take the cores, but instead they did slices. So that was more destructive, but basically gives you the same kind of information. Now we try to steer away from those because it's not really sustainable. We can't go back and sample it again since we've taken it all. So nowadays it's mainly cores. And here you have another image of somebody taking a coral core, just with different equipment, basically. So what information do we get out of this? The main thing, so first of all, when we do the X-ray, we get information about growth of the coral. Here you have a nice regular growth mainly, compared to this one, which is a little bit more all over the place. You can see the pattern is changing a lot. We can also date the coral. So if you know, so this is the top of the coral, this is the bottom of the coral, we know when we sampled it, and then we can count the rings backwards, and we can give it an age. We know the seasonality, whether it's regular or not. The alternation of the dark and white bands gives us this information. And if we look at the fluorescence, so the second image, we get the organic content through that, which comes from floods, eruptions, or dust plumes. Basically, when there's a big flood event, you have all the water that washes the land and goes into the reef. So you get big flood plumes. And the sediments and the organic matter that are contained in these flood plumes go and settle into the reef, and they get incorporated at that time. And that's how you get these really nice fluorescent bands. So they don't necessarily mean flooding, but they mean that there's been something happened at that time. So then we look at the chemical composition. Sorry. We can use the carbon-14 dating as well. So if you have a core that is not very regular in the growth pattern, we would use carbon-14 to make sure that we are dating it right. We use also the oxygen isotopes and the carbon isotopes, not carbon-14, but the other one, to determine sea surface temperature and salinity. This method of getting data was developed in fossil belemnites, which lived 240 million years ago, and they looked like squid. So they had this section here that was made of shell, and as they grew, they incorporated elements from the seawater as well, and that's how the first sort of system was discovered, that we could reconstruct the seawater and oxygen content from the oxygen content of these fossils. That was pretty neat. And then what we can also look at is the other trace elements, like the magnesium, the strontium, barium, uranium, cadmium, boron, and all these can give us different things. So again, we can get the sea surface temperature, we can get the composition of the seawater itself. So if there's been, if it's near an industry that's on the coast, for example, and this industry releases certain chemicals in the atmosphere, and in the water, there's a good chance we can pick it up in the corals. But there's other things, like I said before, the flooding, upwelling, and we can also measure pH. Yes, and because this system is quite complex, we haven't managed to tease out absolutely everything. certain elements that are there, but we're not too sure where they come from and how they relate to the properties of the seawater. So there's still, work to be done on that front. And this whole thing, so it was developed it was first found in the belemnite, but scientists figured out that it was relevant to corals as well, because in the 1960s, a scientist went to collect corals from the Bikini Atolls. And when they looked at the skeleton, they saw some radioactivity. And counting the rings and doing the measurements, they figured that it corresponded exactly to the atomic bomb testing in the Bikini Atoll at the time. So it's a bit sad, but it did help progress on that front. So now I'll take you into a concrete example of how we would use the composition or one of these elements to get a seawater parameter. So here we're going to look at the boron isotope fractionation and pH. So first, isotopes. An isotope is a chemical element with the same number of protons, but a different number of neutrons. A very simple element is hydrogen, where you have one proton, and the hydrogen 1 would be 1 proton, 1 neutron. Hydrogen 2, 1 proton, 2 neutron. Hydrogen 3, 1 proton, 3 neutrons. So if you look at the boron, we are focusing here on the boron 10 and the boron 11. We know that in the seawater, we find boron as boric acid or boric ions. And we also know that the calcium carbonate incorporates boric ions better than incorporates boric acid. And we know how much of those different, the isotopic ratio basically of boron 11 to boron 10 that is found in boric. So if we look at the graph here, on the x-axis you have the pH, and then on the y-axis you have the isotopic ratio. We know the seawater pH because we measured it. So here we are going from a measurement situation where we have already the seawater pH and we have the seawater isotopic ratio of boron. So that gives us this data point. Then we also know the boric ion empirical curve. So that's been determined in the lab by doing many measurements at different pH and different boron levels. So we know how much borate there is because we know the isotopic ratio and the pH. Now, if we work from the coral skeleton, so the coral skeleton, we measure the isotopic ratio, and then we know the borate curve. So that gives us afterwards the seawater pH. The pH can be also higher or lower. It depends. There's a big variation, but it's smaller than that normally. And then there's this third case where you're on site, you have your seawater pH, and you have the pH you measured from your coral skeleton, but they seem to match, but that doesn't fit your curve. So this difference is called the vital effect. It's basically the animal itself that has gone in and tempered with the concentration. So it's different, but it has been quantified in a few different species, in a few different groups. So we're getting better at measuring the vital effect. We haven't fully understood it, but we're working on it and we're trying to get better at it. And then the pH itself, that data is related to ocean acidification, because as the carbon dioxide in the atmosphere dissolves into the ocean, then the pH changes. That's what we want to know. Now, so I've been talking about the corals and the reefs for a while. So we can get data from those sort of tropical, subtropical areas, but how about the rest of the world? Have any of you, do you have an idea of other things that create layers that we could potentially measure? Anybody? No? Wait, I need to open the chat. Let's see the chat. Stacy, maybe can you read are there any answers in the chat?
Absolutely. There's 2 votes for trees.
Okay, trees, nice, you get points. Yes, so the trees totally, it's a slightly different system because they built their the trunk differently. It's not the same, it's not calcium carbonate, basically, that's what I'm getting at. But this system, dendrochronology, is also quite well developed. Then we also have seashells. So seashells create layers as they grow, and we can collect climate data like that. Especially the good thing about them too is that they stay in one place. They don't, move around. Then we have ice cores. So again, it's not the same system because they don't create calcium carbonate, but you can measure the composition of the air bubbles and you can measure the composition of the melted ice. And this one is pretty cool and often surprises people. So fish have an ear bone, a very small ear bone. So you can dissect it, take it out, and it grows in rings just like the corals, just like the trees. And you can measure the composition of each ring, and it tells you sort of where it's been. For example, if you do it in a salmon, you will have the composition of where it started and when it finished. So technically, they migrate, go back to the same place kind of thing. So you would be able to get that. So despite the movement of fish, you can track them through those movements. Then you also have sediment cores. The sediment cores in the ocean, you get them from, and those planktonic organisms. So that means they live in the seawater, in the water column. And these ones build calcium carbonate structures. So as they grow, they build another one that's a different composition from the first one they grew, basically. And when they die, they sink to the bottom. And as they accumulate, that's how you get your cores. And they can go very deep, and you can pretty much get them from nearly everywhere. And then the last one here is stalactites and stalagmites in caves. So they're not living, but they have a similar pattern of sequential accumulation. So as your drip builds up the minerals and runs through the whole system, and it picks up all the minerals, and when it settles somewhere, that's where it leaves the minerals and they attach to the surface. So you can get layers like that. So now if you take a multi-proxy approach, so you put all these together, you get the coral reef data, you get the trees, you get the seashells, you get the fish, you get the ice, you get the sediment cores, and you get your caves. So this, plus all the information from the instruments I mentioned at the beginning, so satellite, weather stations, you get a really much more complete and detailed data set. Once you have all this data, you take it to a supercomputer. Not me, but you have people who have nice fancy supercomputers, and they analyze all this data. And with it, they can make predictions like here. You have the changes in the air temperature over a 100-year period. Just play it again for you guys. It's quite interesting to have. So it's a mixture of data that we've accumulated from the past and stuff that we're predicting from what we already know. And then you have like at the bottom here, you can run predictions. So for example, if you change the amount of carbon dioxide in the atmosphere, because presumably the government would have done something about it, then you have different projections, so different scenarios where the temperature is rising, but rising less fast. And with all this data, we are managing to increase the precision of the predictions of floods, storms, heat waves, and all so not just whether the ecosystem is going to respond well or bad, but also what's going to happen on land to the populations. Now we get extra data also on geological timescales. For example, there is a coral core, so it's not so much geological, but there's a coral core from the Great Barrier Reef in Australia that is so long that we were able to know what the temperature of the seawater was when James Cook crashed his ship in the Great Barrier Reef and landed in Australia. That's quite an interesting fact, and it's like 3 meters long. it's really awesome. But anyway, in terms of geological scale, so we have managed to make predictions, and we've noticed, because we managed to reconstruct past conditions, that the temperature predicted for the future aren't unprecedented. For example, at the Paleocene-Eocene thermal maximum, there was really high temperatures that were, but it was also a global warming event that was attributed to massive methane release. If you're not too sure when that was, so the Paleocene-Eocene, you have this geological scale here. So you have the dinosaur times in the middle here, you have us up there in the Holocene, and the Paleocene-Eocene was about between 66 and 56 million years ago. So that transition. And so it's really interesting to have these comparisons, because we can try to understand what happened then. Back then there was a huge extinction, both on land and in the ocean. So it would be nice if it didn't happen again, but there's not that much we can do. We can slow the rate, but it's hard to stop it. So without getting political, I just want to say that there's a lot of evidence of climate change and global warming. We can't deny it anymore. And like I said, we can't really stop climate change, but we can slow the trends if everybody does a little bit. It's hard to know what exactly you can do, but you can start with being more conscious about your carbon footprint and your waste as well. So on that, I'd like to end, and thank you very much for listening. If you'd like to contact me, you've got my email up there, and I would like to thank Dr. Lewinsky for bringing me to VCU, otherwise I wouldn't be here, and the NSF for project funding, and the VCU Libraries for organizing the How to Talks media series.
Well, thank you so much for this awesome talk. We have a good bit of time for questions, so I think that I'll lead off just because I'm first. So here you've listed these 10 things you can do for trash-free seas, which they all look awesome. If we could start with one thing today, which one would you say we should start with?
Well, just being conscious really of the waste you produce, because especially right now with COVID, it's so easy to think I need to stay home, and then you order food and everything's delivered in all this packaging, and even just going to the supermarket when you buy stuff off the shelf, you know, is it in 10 plastic wrappings, or is it just in one? Are you bringing your own bag, or are you taking the plastic bag from the shop? It's very basic, but being from Europe and having lived in Australia, I've noticed differences in the culture. There's some places that are better at that than others. So sorry to say, Richmond is not very high on the scale of trash conscious.
Mm-hmm.
Maybe I should stop sharing my screen. I can see it in the chat. When I forgot to mention, well, I did say at the beginning, but my next talk will be on the 15th of March, and it will be about using nanoparticles to help coral reefs defend themselves against coral bleaching. So if you have time and you're interested, please join.